All right, welcome back to another video. Big apologies for some of my previous videos. I think this is the best sound I've been getting so far. I hope it's really nice and clear, but unfortunately, if I make a mistake using this microphone, I forget to turn it on, I forget to plug it in, it doesn't fail over to a different kind of microphone. I was kind of assuming it did that, where it would just use my speaker mic and it'd be a little bit worse audio, but you'd still hear me. But what happens is it just drops the audio. So a lot of my old videos just don't have audio for a large section. So yeah, sorry for that. I'm still gonna leave them up. It might be frustrating. Close these. So I've got plenty of pure YouTube poop posted now because you can't even hear me give a networking lesson. So I think if you could actually hear the content, there would be some validity to the videos. But the ones where I have microphone issues, I apologize for. But I'm still kind of just getting off my feet, and I'll reiterate what the main intent of this is. It's just to help me practice and prepare for an exam I plan to take in September. And if along the way I develop really good skills for giving lessons and being a good teacher, that would be wonderful. And I can make maybe a series that is more devoted to that after I finish my journey with this exam. But for now, we're going to learn more about BGP route reflectors. Specifically, in the last video, we're meant to learn about the .3, Inet.3, and the Inet 6.3 routing tables and how they work for route reflectors. There are some issues where if those tables are not populating with routes, you can have reachability issues. So the recommended solution for that is to enable LDP and have that automatically flood those tables with the routes that were in Inet.0. Another solution is to use rib groups to have that table populate. My preferred solution is the one I absolutely can't for the life of me remember, unfortunately, but I saved the thing I read yesterday that goes through them really clearly from Inet.0, and I'm going to start this video by just reviewing that. So you can also use a static route. You can alter default route resolution. Yeah, here's the rib groups. Let's go up to the top where they just list out the methods you can use. Okay, well, it looks like they don't do that, but here's where you can use a label distribution protocol. It's probably the way I do it. It's kind of the one I remembered first. Doesn't seem that difficult. Static route. Now this is what is the easiest way, I think, adding default route resolution. So all you need to do, and this is only something you can do with Junos too, you can't do it with Cisco from what this says. So you just say set routing options resolution rib BGP.L3VPN.0 resolution ribs Inet.0, and you do that on the route reflector. So really easy, one command. And you can even just do that for specific subnets too by filtering out the ones you don't want in the Inet.3 table with a policy statement. So that's probably the easiest way, and it's the yeah, resolution ribs Inet.0. So let's kind of solidify that and find that command resolution ribs. So it's going to be under the BGP group, I believe. This is not responding to my mouse clicks. There we go. Now it is. So, oh, no, it's under routing options. So I think that's probably why it's hard for me to remember this, because it's in a hierarchy that I really haven't been to yet. Routing options resolution, I've really never gone into that hierarchy in Junos OS before. So let's take a look at all the help, question mark everything out. So next hop resolution options, and we know that this is a problem with next hop. There's an issue where if the traffic belongs to a L3 VPN and the routes are exchanged using LDP or BGP, as happens in L3 VPNs, your route reflector will not be able to properly reflect that traffic unless it has the routes in the Inet.3 table or Inet.6.3 table if it's IPv6, as well as the .0 table. And RIB, routing information base. This is just another word for routing table. It's kind of a convenient shorthand for it because routing dash table is a lot of characters and RIB is only 3. So resolution ribs is routing tables to use for default routing table family resolution. There you go. So that's all there is to that. It's not too difficult. It looks like I don't see them in the Inet.3 table though here. So, that's interesting because I was wondering why. I thought it had to go into the .3 table. But as I said before, I think the easiest way to do it, you can always use a static route. This is probably one of the absolute easiest ways because you're calling out the .3 table. So conceptually, we know what we're trying to do, and it involves the .3 table. So calling that out in our command specifically makes it the easiest command to memorize. Yep, but I think the easiest way is just going to be, if I do a rollback 0, it's going to be edit protocols MPLS interface, or actually it's going to be set protocols MPLS interface all, and then set protocols LDP interface all. Now you're going to have that Inet.0 populate with information. So that's all there is to that. The next part I wanted to do is just go through and do the full Juniper documentation on route reflection. Fortunately, that might take me a while, and as we saw in the previous video, I'm really spending too much time on particular things, but let's get started. BGP route reflectors, understanding BGP route reflectors. This topic Discusses using route reflectors to simplify configuration and aid in scaling. A further way to reduce the workload on a route reflector that is not in the traffic forwarding path is to use the no install statement at the edit protocols BGP family name hierarchy level. Starting in JNCIE-SP release 15.1, the no install statement eliminates interaction between the routing protocol's daemon, RPD, and other components in the Juno system, such as the kernel or the distributed firewall daemon, DFWD. This interaction is eliminated by prohibiting any routes in the associated RPD routing information bases, RIBs, also known as routing tables, from being published to those components. Note in releases previous to JNCIE-SP release 15.1, you can reduce the workload on a route reflector that is not in the traffic forwarding path by using a forwarding table export policy that rejects the routes learned from BGP. Because of the internal BGP, IBGP full mesh requirement, most networks use route reflectors to simplify configuration. The formula to compute the number of sessions required for a full mesh is V times V minus 1 divided by 2. So I really don't like it put that way. You can, of course, I forget what property it is. It's called like the associative, no, I think it's called the distributive property of mathematics or arithmetic, the distributive property of arithmetic. I think that's what it's called. One of my life goals has been to get really good at math, because when I went to college after high school, I studied music performance, and I didn't have to take any math after that. And throughout high school, I really enjoyed math as a subject. It was always interesting to me. And, I did pretty well at it, and I just think math has a lot of power in helping you to think and make right decisions. So it's kind of something I wanted to do. So I'm going to take the extra moment to look up. Yep, and I was right. It's called the distributive property. So from that, we know that this can be rewritten as V squared minus V divided by 2. That's the way I like to say it. I don't know why they don't like to say it that way, but, and then V, I don't know what V means, but N or L, because I think it's better to use, because I don't know what V means, but what they're talking about is the number of, okay. They're talking about the number of BGP enabled devices. So D or N, I think would be better than V. But it's D squared minus D, all that divided by 2. So if you got 5, it's going to be 5 squared, 25, minus 5 is 20, divided by 2, you're going to need 10 links. And that number is going to scale up exponentially, I believe. Well, let's do it in Python. So IPython, this is what I love about Python, by the way, too. So we're going to say def scale BGP, and then we're going to give it number of devices. So we're just going to give it a number, and then we're going to say links equals, and then it's going to be number squared divided by, minus number divided by 2. And then we're going to return links. And then let's just go until 1,000. So we're going to say a equals 0, and while a is, oh, well, let's start with one link. A equals 1, while a is less than 1,000. We're going to do scale BGP A, and then we're going to increment A. So I think this will work. Oh, no, because we gotta print this out. Oh, it still didn't work. Oh, duh, okay. Oh, wait, no, that works. This is interesting. What is A? A is 1,000. Oh, because I never reset it. There you go. This should work now. Perfect. So yeah, we can see this number incrementing now. I would like to graph it. Of course, I'm really getting off track here, off topic, but I would really like to. Let's do print result, then a colon, and then let's print A, and then we're gonna have A equal to 1 again. So here it makes sense because you can see, it's not too far-fetched that you'd have 600, or at least it's completely not far-fetched that you'd have 16 routers in your network. So you're really going to have 120 links that it really scales up fast. Yeah, if you have only one device, you don't need any links, but two, it's not scaling up at the same rate of devices. The device, you add one more device, you only have 6 devices, but you need to add 5 more links, 6 more links, 7 more links, and then we're going up to 8 more links, 9 more links, 10 more links, 11 more links. It seems to be, yeah, I wish I could have a, well, let's see here, import MATLAB, or plot, let's see here. So Python plot graph. I think I know how to do this really easy. I'm just going to go to my own GitHub because I have a Gitbutt. Hub. Going to. Okay. So I'll just go to my own GitHub. There it is. So I wrote this software that uses plotting. So it uses graphing. So I'm going to use that. So let's see here. So for I in pattern. Okay, so here we go. Graph data. So PLT, let's see what that is. Aha, here we go. So import MATLAB as PLT. Okay, and now on our x-axis, we're going to want the number of devices. So I don't know what this negative I means, but let's use this. Oh, I know what it means. I turned it into a negative number because I needed to have negative numbers in order for it to go well. And then I'm not sure what that D means too, but yeah, I think this function is going to be fine. We're going to have to go back to our thing here, and we're going to have to return. So we're going to have to define data, of course. So data equals an empty list. And then we're going to fill up that list with tuples, and those are going to be our data points. So the tuple is going to be so A, which is going to be the x-axis, and then our result, which is going to be the y-axis. And it's going to be data.append. There we go. So let's get and let's do A equals 1. And let's say length of data, see if it filled up. Nope, didn't fill up. Okay, now let's do another length of data. So yep, it filled up. Let's graph this out now. So we just need for I in data, graph data I. That should do it. And it's going to be plt. Oh no, graph is defined already. Oh. Oh, right. Oh, so I've got to do for xi in enumerate data graph data x, because I need the oh, actually no, it's going to be for I in data graph I. That should do it. It's an int object. Okay, well, what is I? I is that. So it should be graph I, right? Let's go back to our definition for graph. Here we go. Oh, okay. Yeah. We got to change this definition up. Okay, now we'll have a much better time. So it's working on that. Sweet. So now we can show our graph and we can see how that increases. So you can see, yep, it's an exponential rate of increase. The more routers you add, the more links you need, but where the amount of routers you need just increases linearly, the amount of links you need increases exponentially. So you're really going to run into a number very, very fast of links that is not possible to turn up the more routers you have. So that's why that's why there's a scalability issue in BGP, and you need something like route reflection or route configuration. ISP, it looks like all we're worried about is route reflection, or at least for the purposes of this exam, because route configuration is not on the curriculum. But I think this makes it very clear what the problem is with scalability and BGP. The full mesh model does not scale well. Using a route reflector, you group routers into clusters, which are identified by numeric identifiers unique to the autonomous system, AS. Within the cluster, you must configure a BGP session from a single router, the route reflector, to each internal peer. With this configuration, the iBGP full mesh requirement is met. To use route reflection in an AS, you designate one or more routers as a route reflector, typically one per point of presence, POP. Route reflectors have the special BGP ability to re-advertise routes learned from an internal peer to other internal peers. So rather than requiring all internal peers to be fully meshed with each other, route reflection requires only that the route reflector be fully meshed with all internal peers. The route reflector and all of its internal peers form a cluster shown in figure R1. Yep. So these links here all look like they are virtual links, like they're not actual physical links. That's why you have a route reflector. It can allow you just to have links among these devices and just one, at least one link out to the route reflector physically. And installing links for people brand new to networking is a whole ideal. You've got to bury the links, you've got to get construction permits. It's a construction job. In a lot of cases, installing a link is really an ideal that will delay your project by weeks, if not months. Note, for some Juniper Networks devices, you must have an advanced BGP feature license installed on each device that uses a route reflector. Figure 1 shows a route reflector configured as the route reflector for cluster 127. The other routers are designated internal peers within the cluster. BGP routes are advertised to route reflector by any of the internal peers. RR then re-advertises these routes to other peers within the cluster. You can configure multiple clusters and link them by configuring a full mesh of route reflectors. Figure 2 shows route reflectors RR1, RR2, RR3, and RR4 as fully meshed internal peers. When a router advertises a route to RR1, RR1 re-advertises the route to other route reflectors, which in turn re-advertise the route to the remaining routers within the AS. Route reflection shows the route to be propagated throughout the AS without the scaling problems created by the full mesh requirement. Note, a route reflector that supports multiple clusters does not accept a route within the same cluster ID from a non-client router. Therefore, you must configure a different cluster ID for a redundant route reflector to reflect the route to other clusters. So that's a good point there. Redundant route reflector most cases, just one route reflector is too great of a point of failure to not back up. Otherwise, you're really setting yourself up for a bad situation where your whole network, BGP network, goes down instantly. So you definitely want redundancy on your route reflector just by setting up a second one. However, as clusters become large, a full mesh with a route reflector becomes difficult to scale, as does a full mesh between route reflectors. To help offset this problem, you can group clusters of routers together into clusters of routers for hierarchical route reflection. That's a word I haven't said out loud in a long time. Figure 3 shows RR2, RR3, and RR4 as the route reflectors for clusters 127, 19, and 45 respectively. Rather than fully mesh those route reflectors, the network administrator has configured them as part of another cluster, cluster 6, for which RR1 is the route reflector. When a router advertises a route to RR2, RR2 advertises the route to all the routers within its own cluster and then re-advertises the route to RR1. RR1 re-advertises the route to the routers in its cluster, and those routers propagate the route down through their clusters. All right, so yeah, so let's read the overview for this, and then the next video will dive right into the configuration. Generally, internal BGP, iBGP enabled devices need to be fully meshed because iBGP does not re-advertise updates to other iBGP enabled devices. The full mesh is a logical mesh achieved through configuration of multiple neighbor statements on each iBGP enabled device. The full mesh is not necessarily a physical full mesh. Maintaining a full mesh, logical or physical, does not scale well in large deployments. Figure 4 shows an iBGP network with device A acting as a route reflector. Device B and device C are clients of the route reflector. Device D and device E are outside the cluster, so they are non-clients of the route reflector. On device A, the route reflector, you must form peer relationships with all of the iBGP-enabled devices by including the neighbor statement for the clients, device B and device C, and the non-clients, device D and device E. You must also include the cluster statement and a cluster identifier. The cluster identifier can be any 32-bit value. This example uses loopback interface, the loopback interface IP address of the route reflector. On device B and device C, the route reflector clients, you only need one neighbor statement that forms a peer relationship with the route reflector, device A. On device D and device E, the non-clients, you need a neighbor statement for each non-client device, D to E and E to D. You also need a neighbor statement for the route reflector, D to A and E to A. Device D and device E do not need neighbor statements for the client devices, device B and device C. Tip: device D and device E are considered to be non-clients because they have explicitly configured peer relationships with each other. To make them RR route reflector clients, remove the neighbor 192.168.5.5 statement from the configuration on device D, and remove the neighbor 192.168.0.1 statement from the configuration on device E. So here's our topology. You can see I've got that set up in the lab. So unfortunately, I need a little bit of a break before going on. Let's do our 5 problems from subnetting.net today, and then call it a completed video. And again, I do apologize for my issues with sound in my earlier videos. I have adopted a new technique where whenever I'm just using Zoom to record these videos. So I'm going to test the sound, the mic and the audio before I hit record every time to make sure that I'm actually not going to be producing those videos with no sound anymore. So if you like those videos, I apologize for that too, because you will not be seeing those anymore. Okay, so this is going to be every 32. So 128 is a kind of sticky number. So 160 is another one. So the first valid host is going to be 161. So that's one finished. So now we need the broadcast address, 172.27. So 19, that's going to fall within the second subnet. So 16, 17, 18, 19, these bits are all going to be off. So we're just going to turn the rest of the bits on. This is the 128.64.32, so it's going to be .31.255. All right, so you need a third one, the subnet this host belongs to. And it's a /23. So okay, so it's going to be .28.0. And the reason I know that is because it's a /23, which means all bits except for the last one are going to belong to the networking portion. And if the last bit is toggled on, you have an even number. Sorry, you have an odd number in decimal. And if it is off, you have an even number in decimal. And when you toggle it, if it's already on and you toggle it off, you're going to have a lower number. So I know it's going to be 238 right off the bat, real easy, because I know it's a /23 and there's just one bit in the third octet that belongs to the host address field. And since we're going to enter the subnet, we're going to toggle that bit off. So I think that was 4. Let's do 2 more just to make sure, in case that was the third one. I wasn't keeping track. And this one's super easy. So yeah, let's do this one and one more. /24, that's a freebie. Should be able to get that right away. So let's do one final one. Oh, and this is one of these kind of more difficult ones where I'm not sure what they're assuming is the initial starting subnet mask. I think they're assuming it's this /16. So out of this, what subnet can you get out of this supernet, this /16, which is the class B private space? Which is the class B space. The private space would be /12, so that you can get 30 subnets. So if you gave it one more bit, you get 2 subnets. So let's see how many more bits we got to get. We got to get 2, 4, 6, 18, 32. So we need 5 more bits. So that's going to take this out to a /21. So it's going to be 255.255, and then 20 would be 248. So it's 240. So it's going to be 248.0 because 21 falls within the third octet. Sweet, and we got all 5 or 6. I don't know how many we did right. So let's end the video, and then when we come back, we'll be doing the hands-on exercise for BGP route reflection. So stay tuned.